Hey, it's like Saturday night enough that it's dark in here and I haven't turned on the lights because I've been working on the notes for this week. In any event, I was going through some of the assignments that you're going to be facing this week, and I noticed a couple questions that I wrote for Honors Pre-Cal a couple of years ago, I think back in 2017, summer of 2017. And I remembered that in 2020 and 2021, when I taught Honors Pre-Cal, my students had a lot of trouble with them. And so I thought what I might do is just quickly create some video solutions to talk through those problems, so that way you can have some support while you're working on them, because they definitely feel like the sort of thing that could show up on a test in that next unit exam that we're going to take. So in any event, I'm going to be focusing on question number 12, as the screen above me or around me probably indicates. These questions focus on using the algebraic definition of even and odd. So the algebraic definition of even and odd. And what I'm going to do is I'm going to do a couple of the problems from the assignment itself, but I'm going to leave you a few of them. But in exchange, I'm going to start with a couple made-up examples to help you see what's happening here and to kind of illustrate what it's going to look like when you actually do this stuff. So without further ado, let me go ahead and kick that off here with just kind of a discussion about 12a, and then I'll do those like extra examples to illustrate what's happening. So in number 12, it tells us two things. It tells us that first, e of x is an even function. That makes sense. That's pretty easy to be able to hold on to, e for even. And O of x is an odd function. Also, when I see that, I see ox, and I think of oxen and fjording the Oregon Trail and all that stuff for whatever reason. More relevant, though, it tells us in part A to use logic to evaluate e of negative x and O of negative x. And the fact is, it all kind of comes down to these definitions here. So we're talking about an even function e of x, which is e to the e of excellent, for us to go through. But remember, algebraically, an even function is a function f such that f of negative x is equal to f of x. And to remind you why that is, remember that even functions have this nice symmetry across the y-axis. So the idea is whatever your y value is on the right side, you're going to have the exact same y value on the left side. It's just if your x value is c on the right side, it's going to be negative c on the left. But they'll have the exact same y values. Same y values is just like saying when you plug negative x in, you'll get the exact same y value, because you'll just move to the other side of the y-axis. So that is the definition of even. Based on that information, we can very easily say that e of negative x is going to be equal to e of x. Like, that's simply what the definition of even says. So I don't know that I would use logic to describe it. It's not just logic, it's using the definition of even. So the algebraic definition of even. On the flip side, we can get that kooky odd function. So the odd function, if you'll recall, is the one that says when you plug in negative x, aka f of negative x, is going to equal negative f of x. And this one feels a little bit stranger, but once again, I think a quick little diagram does the trick for you. So let's imagine once again we have some point over here at c. Well, remember, an odd function, graphically speaking, of course, graphically speaking, has this rotational symmetry. So a point up in that first quadrant is going to end up down in the third quadrant. You can probably see where I'm going from here. Let's say that the y value up here is, let's say, 5. When we do that rotation, that 180-degree rotation about the origin, we're going to end up right down here. The value will, of course, be negative c, because that part hasn't changed. And the height will be negative 5. Again, in this just made-up example. That's because what happens is when we switch the sides here, when we switch from x to negative x, we have to also flip. So it's a reflect and flip. That's exactly what we're seeing happen here. So based on that definition, if O of negative x is for an odd function O, then an odd function says the negative sort of comes out in front. We multiply the original O of x by negative 1, excuse me. So there we go. There are our two pieces for part A. And now I'm going to actually copy these, because these become, from part A going forward, our sort of ciphers, our translation, our code breaking, haven't watched the Da Vinci Code in a long enough time. I'm trying to think of all my words for, like, code busters. I'm making stuff up at this point. We're going to use these in the next few problems. As I said, though, I want to make sure to leave you some of these to be able to work through on your own. So I made up two problems to illustrate how this works before we start. And I'm just going to tack over here on the side, just kind of right above my head, which I think is about right down there. I'm going to put those two little pieces. So as I said, these are not on your assignment. They're just sort of quick examples that we can do that illustrate what's happening here that let me talk through the process you're going to be doing on questions 12A through E. So here we go. So same exact instruction, or what's called the same stem. We're working on the same part here. If f of x is equal to x squared times e of x, so we go ahead and underline that. That's our new function. We're talking about f of x equals x squared e of x plus 4. Is f even, odd, or neither? So based on that question, the fact that we're trying to determine if the function is even, odd, or neither, that's going to be code for us having to plug in negative x. And the reason for that is, it sounds sort of condescending. Just look at the definitions. Both of them require us to plug in negative x in order to determine that answer. So that's exactly what I'm going to do. I'm going to plug in negative x and see what happens to my function. Then I'll compare it to these definitions that we have. So watch closely here. I'm going to calculate f of negative x. I'm hoping it becomes one of these two things, but even that we don't have to think about. If I plug in negative x, I'm going to plug negative x squared times e of negative x, and then plus 4. So that's it right there. We've plugged in negative x. Now, of course, plugging it in is different than actually evaluating it. We are going to have to go a little bit further to see what we get out of this result. So looking at this, negative x squared is just going to be x squared. And then here's the key part. E of negative x, according to what we did here with the definition of even, is going to just be e of x. So that's going to be x squared times e of x. And then finally, plus 4 remains exactly the same. So what we've just shown is that f of negative x is exactly the same thing as x squared times e to the x plus 4, or e of x plus 4. Now this is sort of interesting. In your mind you might be thinking, hey, haven't I seen that before? And the answer is yeah. Heck yeah, you have. That's exactly where we started. This thing is equal to f of x. So in other words, what we have just shown is that f of negative x is equal to f of x. Now what does that mean? Well, if you get the exact same y value out from plugging in negative x as x, that tells you that we therefore have, in this case, f of x is an even function. And actually I'm not going to write and, I'm just going to write is even. So we have just proven the function is even, because that is the algebraic definition of even. F of negative x equals f of x. In fact, it's the same letter because I chose the same one. So there it is. There's our process. We plug in negative x, and then we see what happens. Let me illustrate that one more time. The second made-up problem, again, I'll do a couple real ones, but these are the made-up ones first. So our second made-up problem here, and I'll, again, translate in those little pieces, or paste in those little pieces here. So in looking here, we have g of x in this case. Gee, that should be interesting. 5x minus o of x. And the question is g of x even, odd, or neither? Well, as we said before, our process is consistent. To determine that answer, we have to plug in negative x and see what happens. See what ends up with our function. So in here, we're going to plug in negative x to g of x. That's going to be 5 times negative x minus o of negative x. Again, it's just a step. But again, if you're thinking in terms of tests, that's a point. Just plug in negative x, you get a point. It's a good thing. You like points, don't you? So from here, what does this simplify to? We're going to clean it up a little bit. Well, 5 times negative x is the same thing as negative 5x. And then over here's where we got to get creative. So ignoring that minus sign for a second, although I probably shouldn't completely ignore it, I'll put it right in here. O of negative x, we have that already out. We saw, using the definition of an odd function, that o of negative x is equal to negative o of x. So I'm going to plug in here negative o of x. Now, of course, I can simplify that a little bit, and I'm going to. This is negative 5x, and then the second term is negative times negative, or positive, o of x. Now, this is a little bit harder to see. I've chosen one. This would be a tough one. Trust me, this would be a difficult problem to give you, especially as our second example. But looking at this, what we need to do is we need to see how this compares to the original. On the previous problem, we were able to see that, oh, f of negative x is equal to f of x. We clearly knew it was even. In order to determine if something's odd, we need to factor out a negative sign. Or if you want to think about it better, we need to factor out negative 1. So that way we can pull that negative out in front and see what function's left over, to see if maybe that's the original o of x. So here's what we're going to do. Pull out that GCF of negative 1. I'll just write it as a minus sign. If I pull out a negative sign from 5x, that's going to be 5x. And if I pull out a negative sign from positive O of x, that's going to become negative O of x. So what we just found is that g of negative x, I should write that in here, g of negative x is negative 5x minus O of x. And here's the thing, we've seen that before. Deja vu. 5x minus O of x is g of x. So in other words, we just showed, can't forget that negative sign, we just showed that g of negative x is equal to negative g of x. That tells us g is odd. Because odd functions are the ones that, when you plug in negative x, it spits out the original function times negative 1. That way we get the flip and rotation, or the flip and reflection that we were talking about. The double reflection, I think that's it. So there we go. There's your process. Once again, you're plugging in negative x, you're GCFing, maneuvering, manipulating until you get to your value. So let's try it with the next two. I think it's only the next two that I have in here, but we'll at least take a shot at it. So I'm just going to pop these up in the corner. So for part B on yours, this is the actual one you have on your page. Let t of x equal e of x plus 7. So I'm going to be prepared here. So t of x. We want to figure out is t of x even, odd, or neither. Provide a reason. Okay, well we've done this before. To determine if something's even, odd, or neither, we're going to plug in negative x. That means we're going to plug in negative x to e, and then 7 has nowhere to plug in, so it's just plus 7. Fair enough? Yeah. So from here we need to evaluate e of negative x. But again, just as I said in those previous extra examples, we know e of negative x is equal to e of x. That's what the definition of even means. So let's go ahead and make that fix. E of negative x is just e of x. Everything else here stays exactly the same. So t of negative x is equal to e of x plus 7. Now doing it one more time, where have we seen that before? Well, t of x is equal to e of x plus 7. And e of x plus 7 is sitting right here. That is literally equal to t of x. So we have just shown t of negative x equals t of x. Therefore, those three dots mean therefore, t is even. Because even functions are the ones where if you plug in negative x, you get the original function. Fair enough. And I think this is our last one. Yep. Final one I'm going to do. This was just a lark because I had a few minutes of time and I thought it would be a good idea. So our final one, we're going to do C. The final one I'm going to help you with. You'll still have a few more to do to play with and get to test out. So u of x is O of x minus 6. Is u of x even, odd, or neither? I think this is a good one to wrap up on. So first and foremost, if you want to figure out even, odd, or neither, you better get used to how you like the function. You better get used to plugging in negative x. So when I do that, I get u of negative x is O of negative x minus 6. So nothing weird there. The next move, as you've probably come to expect at this point, is to look at and think, well, what is O of negative x? Well, based on O of x being an odd function, we determined that O of negative x has to be equal to negative O of x. So that means that I can rewrite O of negative x as negative O of x. Everything else here stays exactly the same. So there's what we end up with. We end up with negative O of x minus 6. And now I bet, as you look at this, you're like, oh, we got a negative sign out front. It must be odd. Not so fast, my friend. So I'm going to do that same thing we did on the earlier extra example. I noticed that there's a negative sign in both O of x and negative 6. So I'm going to pull out that negative sign, or pull out that negative 1. That'll leave me with O of x plus 6. So we have just shown that u of negative x is equal to negative O of x plus 6. But here's the thing. O of x plus 6 is not what we started with. It's just not the same thing. That one had a minus 6. I would circle it. This one has a plus 6. Meaning this does not equal negative u of x. So in that case, if u of negative x doesn't equal negative u of x is not odd. And since it's definitely not equal to the original u of x either, so we could even say that, it's clearly not equal to u of x, then that means that our function is neither odd nor even. That means, therefore, u of x is neither. It's neither odd nor even. And if you'd like to say the whole thing, of course you can. Don't be my guest. Be my guest. The service to the test. Da, 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 da. You get the idea. So again, the idea here is using those definitions of even and odd, plugging in negative x to whatever the expression looks like, using what we know about O and odds, evenness and oddness, or oddness and evenness respectively, and then making some evaluation using those definitions to see whether your new function is even, odd, or neither. And we got a couple good examples in here. So just to reiterate, I did problems A, B, and C. I also did 2 extra examples that I think do a nice job of illustrating some stuff. I'm hoping this was a useful little tool to throw at you. If not, well, I'm going to bed anyway. So, good stuff. Have a good night, everybody. And again, yeah, thanks for watching.